Your Assistant Professor, Biomedical Engineering Department in SNS College of Technology. In this video, we are going to see about the continuation of the previous video where we are talking about the PN junction diodes and the applications of the PN junction diodes and semiconductor. What is semiconductor and what are the types of semiconductor we have in it? Here it is a semiconductor fundamentals. Okay, intrinsic versus extrinsic. As we all know that we have two types of semiconductors. That is, one is intrinsic semiconductor, another one is extrinsic semiconductor, where intrinsic is a pure form of semiconductor, whereas the extrinsic is the impure form of semiconductor. Intrinsic semiconductor, that is pure silicon or a germanium, exhibits equal concentration of electrons and holes. At room temperature, thermal energy creates electron-hole pairs, providing limited conductivity. Okay, whereas in the extrinsic semiconductor results from controlling doping, introducing impurities atoms to dramatically alter electrical properties, where the impurity atoms are added into the extrinsic semiconductor, where we can change the electrical properties by adding the impurities into it. In this we have two types, that is N-type and a P-type. N-type, doping with pentavalent atoms, that is phosphorus, arsenic, provides excess electrons as majority carriers. Okay. Next is P-type, doping with trivalent atoms, boron and gallium, creates holes as majority carriers. N-type semiconductor, they provides electrons as majority carriers, whereas in the P-type they are trivalent impurities which creates holes as majority carriers. The Fermi level shift towards the conduction band in N-type and towards the valence band in the P-type material fundamentally changes conductivity characteristics. The Fermi level shift, that is from conduction band in the N-type to the valence band in the P-type material. This changes the conductivity characteristics of a material. Formation of PN junction, depletion region, and a built-in potential or a barrier potential. How does it forms? As I told you already, the P-type and N-type semiconductor combine together to form a PN junction diode, and then when we give an external supply to the circuit, the P-type semiconductor, which contains holes as a majority carriers, and the N-type semiconductor, which contains electrons as the majority carriers. These two, when external supply is given to the circuit, okay, this both will get into a electron hole recombination. It will combine together to form an electron hole recombination process takes place there. Once if the electron hole recombination takes place, there forms a region called a depletion region, a region that between the P-type and the N-type we have a layer called a depletion layer, where the whole electron and hole recombination takes place with a higher potential. Okay, this is the region called depletion region or a built-in potential. Okay, when P-type and N-type semiconductors are metallurgically joined, and fascinating phenomena occur at the junction. Free electrons from the N region diffuses into the P region, while holes moves in the opposite direction. This carrier diffusion creates a region depletion of mobile charge carriers near the junction. Okay, diffusion current, electric field formation, and equilibrium state. Diffusion current, how does the diffusion current forms? Driven by concentration gradient, majority carriers across the junction, leaving behind immobile ionized atoms, where the majority carriers are located or placed near the junctions, where they are where remaining immobile ions will be placed in the P-type and also in the N-types. Okay, where when the electrons and holes recombination occurs, there will be a free space, right? That free space is converted into an atom, ionized atoms. That these ionized atoms are called immobile ionized atoms. Okay. Electric field formation. Exposed ions creates an internal electric field opposing future diffusions. Equilibrium state, drift current equally diffusion current equals diffusion current. Drift current equals the diffusion current, where the barrier potential V naught is approximately equal to 0.7 volt for silicon and 0.3 volt for germanium established. With semiconductors, the main two semiconductors are the germanium and the silicon, where the germanium have the 0.3 volt of barrier potential and where silicon have 0.7 of barrier potential. Okay. Next is the biasing conditions and the IV characteristics, that is voltage to current characteristics. Voltage to current characteristics. A forward bias operation and the reverse bias operation. We have forward bias condition and the reverse bias condition, where in the forward bias the P side, that is P type material is connected to a positive terminal, whereas in the reverse bias the N type is connected in the positive terminal. Okay, here that is VI characteristics, that is voltage and current characteristics, where in the forward bias, as the voltage increases, the current also increases. In reverse bias, as the voltage decreases, current also decreases due to the depletion region, the electron hole recombinations and the depletion regions. Okay. Biomedical applications. What are the applications of PN junction diode specifically? Pulse oximeters, which is used to analyze the heart rate, oxygen level, even heart rate is measured in it. Okay. Power rectifications. Power rectification circuit, that is bridge rectifiers. Specifically, the rectifiers are used for ECG and EEG signals, to analyze the ECG and EEG signals. And next is biosensing. Biosensing, that photodiodes is a biosensor. And fourth one is the laser therapy. Laser therapy treatments are done which helps in analyzing the circuit. Biomedical applications. What are the biomedical applications? Are specifically designed for designed with the help of PN junction diode is that the pulse oximeters, power rectifications, biosensing and laser therapies. These are the main biomedical applications of PN junction diode. Thank you.